Kolby, thank you so much for being here. Folks, we have Kolby here from Ream, Lean Consensus Client, implementing the Rust called Ream, um, a core developer who actually went through the program before it was called EPF. He was working on Portal Network in Ethereum Foundation and now on the future of Ethereum in Lean. Yeah, it's very exciting. We had some general intro to Lean before, so now looking into the actual fundamentals of how it works, how it's implemented. It's very exciting. Thank you so much for joining us. And we have 27 people, so I think ready to start. Awesome.
Oh, for sure. Great. So I guess I'm going to be giving, uh, a presentation on lean client architecture. Never done this before, but how hard can it be? So I guess going on to the agenda, some quick jot notes of what I'll be going over is like the lean roadmap context. What are we trying to achieve with this? What are we trying to change with client architecture? DevNet history, how we've been iterating over like the last year and last few months. Reams architecture, how do we take the spec and I guess put into an actual client we're testing on DevNets? Protocol execution path, like what are we doing in these 4 second slots? Um, how we're evolving in recent DevNet. So currently we're testing DevNet 3 and we're currently in the process of implementing DevNet 4. Uh, why do these like recent changes matter to implementers and why are we doing it? And then like we could possibly do some discussions if we have extra time. So why lean consensus exists. So uh, I believe it was over around like a year and 6 months ago, Justin Drake, one of the main researchers at the EF, basically had this idea of what if we could basically uh, get Ethereum to this optimal state with threats along the line, such as like quantum computers. Could we get Ethereum to the state where it's like stable and it wouldn't have these looming threats? But also, like over the last 10 years of Ethereum, we also got a much better idea of what we want from the protocol. So could we design like this optimal protocol? And over the last year, like how we thought of this and like the movement has changed over time. For example, originally it was called Beam, and then there was like a potential lawsuit, so we changed it to the Lean chain, uh, where originally Beam was quite focused on the consensus layer. It moved to this like idea of a lean Ethereum
Colby,
where it was like, oh,
sorry to interrupt. Can you just click on the slide? Yeah, now. I think it wasn't changing the slides. Yeah, yeah, yeah. I wasn't sure if you were
oh,
speaking on the same slide. We were just on the first one.
oh, sorry.
So maybe we are seeing the different version. Now we are seeing the why Lean exists. Before we just saw the intro. I guess you were sharing not the presentation, but this window. Yeah. Go ahead. Yeah.
Yeah, sorry about that. I'll just share this. It should be fine. Uh, so the idea became like, what if we could simplify Ethereum? One of the benefits of this, alongside like securing Ethereum in a post-quantum way, is the less lines and the simpler Ethereum is, the easier it is to like formally verify and audit, which just builds confidence in this finalization layer, which is Ethereum. So a few concepts that we want to achieve in this like optimal or plan of sorts would be like fast finality, PQ signatures. We want to get ahead of quantum computers because once that is a thing, it's kind of like a bust moment almost. A ZK friendly path. Some of the technical decisions in the past don't work, like aren't totally friendly with ZK VMs. And then like how does this formulate into an actual client? Okay. So current so our current focus is basically like, I think I'll just skip this. Yeah. Uh so we started off in DevNet 0 and now we're about to start DevNet 4 DevNets. DevNet Zero was just trying to get clients working at all. We took a modified three like three a three block like state finality implementation made by Vitalik. We chose this just because we wanted to get something working. There's talks to change the consensus mechanism we're testing with, along with many other parts of the stack. But originally in this DevNet Zero, it was just like, can we interop at all just to get the ball rolling? And then the ideology behind all the DevNets is, can we make this incremental change? So through every single DevNet, we can basically like benchmark where we're at and then make an incremental change. And the hope is that we can do these incremental changes really quickly and quickly iterate and learn from any mistakes we made. So going into DevNet 1, it was integrating lean sig signatures. So it's like, for the first time, we're actually using post-quantum signatures for signing and verifying blocks, which was pretty cool, and testing that on a DevNet. The second DevNet was aggregating those post-quantum signatures. So one of the challenges with post-quantum signatures is often they're quite large. So to actually be able to put them in the block, you need a so in current day beacon chain, you basically uh, validators on the chain, they attest to the block with a BLS signature. BLS is very aggregatable, but the question is, how do we do this in a post-quantum world? And the conclusion we basically came to so far is using a very minimal ZKVM to basically aggregate these post-quantum signatures into a single proof, which is reasonable to fit in a block. Which makes it a lot easier, which makes it a lot more capable of actually scaling the network. So instead of us including every single PQ signature in a block, what we'd do instead is we would propagate them on the network. Then an aggregator would aggregate them all into one signature, and then we'd include that minimal signature in the block, fairly similar to what the beacon chain does with BLS, as I said before. DevNet 3 was turning this into a separate role. So instead of the block builder being responsible for both the task of building the block, but also aggregating the block, what if we had these as different roles? I believe that there's a few EAPs and research paths wanting to do this on Beacon, but the idea behind this is if we specialize roles, these actors can execute on these roles much more efficiently. So, and then for the fourth DevNet is one of the problem with aggregating is we can only aggregate so many signatures per a second. So if we aggregate the aggregations, then we could potentially have like n committees of aggregators at one layer. And then at the next interval tick of the slot, we can basically aggregate all those together. And through that, we could have a much bigger validator base than what we could support if we only had one aggregation layer. So let's say at one aggregation layer, we can only handle 50 validators. If we have 10 aggregators aggregating like 10 committees of 50 people, you could see that you can include much more validators into the set, which is very ideal if you want a decentralized validator set. So what is re-improving? So one thing we're working towards is building like a modular node where it's very easy to switch out these different pieces. One of the reasons for that is because a lot of our work currently is, do I have water? So one of the core tasks is just making changes. Potentially, we would want to completely switch out the networking stack or the consensus stack we're testing with. Both of those are research paths that are currently underway by teams at the EF in terms of research. So a real life, I guess, cycle of the client is we have the lean spec where we basically like decide what we want to do for the next DevNet, and then we work towards implementing that in a client with the goal of interoping with other teams and then verifying if our expectations of the research form reality. Um, and then, so we want to iterate through DevNets fast, but oftentimes these changes are breaking. So trying to interop with like multiple teams has sometimes, I guess, formed like friction, which is one of the challenges. And then, yeah, I think that is good. So Ream at a glance, if we like kind of break it into pieces, is it first off, we have like a CLI where we input all the validators we want to run for the DevNet. This for example, this could be like Genesis checkpoint we want to sync to, or it could be like the current Genesis we're starting from. It will be like a list of all the validators to build that state into, and CLI options so we can connect to all the other nodes running in the DevNet. We have a store of all the information we need. This can include blocks, pending attestations, and other such data. We have an RPC like you would see on the beacon chain. This is just so we can probe the node, understand it, build tooling to better understand the devnets and debug things, which is quite useful. Uh, like the beacon chain, we currently have a networking stack, which is almost identically the same. We just gossip different topics. And for the request response, we have like instead of a beacon block, we're gossiping a lean block. And that is per DevNet, we will have different blocks being used. Coordinating our node. In Ream, we have like a lean chain service, which just processes the blocks. It processes attestations. It handles syncing. So we have two forms of sync. We're either forward syncing, so we're trying to catch up to the chain, or we're like syncing the present chain, which is currently in since DevNet 3 and going on to 4, we have 5 intervals per slot. So if a slot's 4 seconds, you break that up into 5, and then there's different jobs we do in each of those intervals, similar to the beacon chain. So basically, like handling those and coordinating those. And then we also have a validator service, which handles like proposing the block, attestations, and it also handles creating like the aggregations, depending on if that validator has those specific roles on that block. And then to communicate between these services, we just have channels in Rust, um, which is pretty similar to channels in Golang. And I have no clue how C or Zig implements that kind of thing. So how do these services interact? So we have like our lean chain in the center, kind of like coordinating these duties. The validator service acts fairly independently. It's basically probing the chain, very similar to the beacon chain. And then we also have our networking stack, which is sometimes sending requests to our node, or sometimes we're requesting things from other nodes to it. And then, of course, we have our store where we store blocks, and we also have an RPC, so us humans can actually tell what the node is doing. A typical boot sequence will look like we're loading a config. Whoever, depending on the config, we'll either do the Genesis path where we're trying to start the chain from the beginning, or we'll try to checkpoint sync so we can quickly catch up to the chain. After that, we basically like build the anchor. So like the Genesis we're syncing from, if it's checkpoint sync, all we basically do is we take the information of a trusted node, the same as the beacon chain would, and we basically just create an anchor we consider Genesis that we would sync from. So we have these two paths, and after that, we would spawn our node. So the core staying consensus model is you have like lean consensus at like the lean state at the top, which would contain like all the core types, like block, block headers, justified or finalized checkpoints, the validator objects, for example. Uh, we then have envelopes that we would like send over the network and sign. Uh, validator, let's see. Validator records are just like stored internally, which we'd bootstrap from the config. And then we also have feature gates, which I'll go upon later. But creating devnets, there's different strategies that we might pick upon. For example, in Rust, there's features flags, but other clients also use branches to manage their development between forks. And there's also another route of generics, which production clients would often use in scenarios like this. There's trade-offs to all, and I'll go over them later in the slides. So the lean chain service, you could think of it as it accepts the processing of incoming blocks. It accepts incoming transactions. It accepts like incoming, like basically like checkpoints from other nodes. And through that, we update our internal image of the chain. And we're also able to provide this information to us like researchers and developers through the RPC. And then we also have like, it also manages sync and such. The validator provides multiple service depending on the duties of the node, which can depend on the block or the node itself. So for example, on tick 1 in the slot, assuming the validator is responsible for creating a block, we would basically ask the chain service to create a block. Once we get that, we would do all the signing required by our validator and we'd send it off to the network. On tick 1, if we are in a tester for like that selective block, we'll like ask the chain to basically like for the information we need to attest to it, the chain service, and then we'll like vote and we'll send that to the network. And then on tick 2, if you're an aggregator, which is a special role that is opt into, every block you'll basically like, you'll read the block, you'll read all the attestations, you'll combine all the attestations, and then you'll gossip that proof to the rest of the network. So it can basically like formalize that block as valid and attested by a 2/3 majority of the network. So our typical networking path is we have like the lean chain service and we get gossips through the network, we get requests, we get it receives like potential checkpoint sync information that we might need. And then we also have a message bus where the validator service or the chain service might be like requesting information through these different channels. So conceptually, it starts out with just a config, which defines everything we need from the service. We create the service object, which manages those different, like discovery of other nodes, gossip, requesting or responding like blocks or statuses of nodes, and then routing these messages between the services. Below that, we have basically like a behavior, which is basically like an implementation, what like defines how we handle these protocols. And then below that, we have basically a libp2p swarm. This stack is what you would basically see on any beacon node today. One interesting note is currently there's in the work to have like an optimized peer-to-peer stack just for Ethereum. And the conceptual idea behind that is libp2p is a generic framework. What if we could build a framework specifically for Ethereum? This stack is likely to be adopted by the beacon chain or whatever ends up, or whatever it becomes, who knows? And also the execution layer. It's meant to be an optimized stack and potentially like our teams would be testing that and prototyping that first. So potentially we'll like completely swap these two layers out with something the EF P2P research team is working on in the upcoming months. So in the earlier slides, I basically like touched a few of the ideas of like jobs we do at certain intervals, but can we, I guess, like formalize that so it's a lot more clear? So we have interval 0, 1, 2, 3, and 4. And what are the basic, I guess, roles or priorities of each of those intervals? So an interval 0 would be proposing a block, which would be done by a validator what was selected on that block. Similar to the beacon chain, we would have an attestation interval, an aggregation interval. We would update our targets, and then we would also like intake the attestations at the end. Potentially, we'll also add an interval for like recursively aggregating the aggregations on DevNet 4. But this one basically outlines the basic idea of DevNet 3, and these ideas also should map fairly well to the beacon chain as well. So if we are the proposer, how does that kind of look? So the thought starts, our validator service requests the chain service to like, hey, build a block. The validator service then gets that back. We sign and publish the block. That propagates through the network, and later that's attested to, aggregated, and we basically have a new block added to the chain. If we're not the proposer, well then currently in all our devnets, every node acts as a validator. So what we basically do is we receive the block, we verify it and store it. We attest to it at interval 1. We gossip our vote to the network. And then after that, the aggregator aggregates that all and shares the proof to the network. And then we formalize that validated block onto the chain. And how would this look if we were the aggregator? Well, the aggregator watches the subnets for votes. In DevNet 3, that's basically like one committee, but in the future, like the network would be split into multiple subnets. It basically gets all the votes for its committee, it builds the aggregate proof, and then it gossips it to the network, and then all the nodes on the network would like update their like head target and like the safe target and finalization target. So fork choice and aggregation. So fork choice, it tracks the blockchain. It decides what is the safe target. It basically determines like what is like the weight of the votes for each block. Our aggregation path is basically like counting all those votes, building it into one aggregate, validating that, and then pushing it to the network. The goal would basically be for like specialized roles to be more common throughout the network, where currently the beacon chain is very singular. I guess we do have validators and we do have block builders. Over time, that should just be more enshrined in more specialized roles, dedicated to special parties who can best handle that. And then architectural lessons. Many of the lessons and the ways we're building clients has been learned from the beacon chain. Hopefully we can iterate and like figure out good ways to solve these problems so that like when it is ready for production, we basically have like a good heading in how we should solve and design like the code and research behind that. So I've talked a lot about DevNet 3 and DevNet 4, but to be very succinct, DevNet 3 signed blocks include the proposer attestation, basically every single validator has a single key, and then older proposers, and then it's like we basically include like the aggregation proposal like into the final block, so it's a lot more compact than DevNet 2. And then in DevNet 4, we're basically making it so the block containers stand alone. We're separating attestations and proposer keys. Block root, yeah, block proposers will sign the block roots, and it's basically just a cleaner path, which will allow us to achieve recursive aggregation on that DevNet. So why did we? So for a lot of the lean clients, we're like the goal is to quickly iterate through these research concepts so we can try to form this like minimal optimal state and ship it to Ethereum. So why did our team choose separate branches to architect this feature? Or no, why did our team choose like Rust feature flags instead of stuff like separate branches and generics like other teams sometimes have chose? So for separate branches, one of the challenges you do is you basically need to maintain two branches for the lifetime of both those branches. Well, at first it looks simple. Oftentimes, if you want to fix, you'll need to port it between both, and these branches will also diverge more and more over time. So applying these fixes from either like upstream or fixes elsewhere become a lot harder to track. Generics are good, and we use generics when we want to basically test between two different like cryptography libraries, for example. But using generics this early on for different devnets, for example, like for defining differences between the state, is a really high cost. So that's often done in beacon chain clients because there's a lot of maturity around like the protocol. But for quickly iterating on devnets, where we might just throw away the consensus layer code or the P2P code as a whole and rewrite it, which currently there are research paths to do that. Generics are a really big cost when we don't know the future. So Rust flags are really nice because we can basically have like one branch, and we can basically be super explicit on what code will run on one devnet, one code that will run on another. And then when we're done with an old devnet, we can just basically like regex delete all the old code, bump the next devnet to the default flag, and then we can start working on the other one. So it allows us to execute on these devnets a lot more quicker, which is super nice. So where does ZK and Lean VM enter the stack? So for this case, for the single validators, we're using, let's see. I need to check the name quick because it's long. But let's see. So we're using hash-based like multi-signatures, which basically this is like a hashing scheme, which can take like any like signature, like hashing fundamental. For example, in our case, we're using Poseidon. There's some work underway to switch like what version of Poseidon we're using. There was sometimes talks of using like SHA-256, but currently the belief is Poseidon is like the most efficient hashing algorithm to be done on ZK VMs. So, okay, let me switch back to the slides. So each validator first attests to the block with this like hash-based scheme, but then after that, what we do is we basically aggregate it using a minimal ZK VM, which the repo is called lean multisig, but the specific package we use is lean VM, which I believe uses Starks, but that's more of a researcher question. I don't really work on that part, but yeah. So how does Ream integrate this? I was saying this earlier throughout the talk, but basically the validator service basically handles like the signing of like these hash-based signatures, which would be lean sig, which is basically like you could think of it like a tree where you basically just like create a ton of like Poseidon hashes throughout the tree, and then you use a leaf of it to basically like sign a block, which is like the most simple way you could think of it possibly, and kind of a wrong explanation, but it's good enough to understand that. Lean multisig is the minimal ZK VM, which aggregates these signatures. The difference between these is basically like this is the main repo. It has extra packages. This is what we use directly, and then like integrating this all into the client. So aggregation and attesting to blocks is done by the validator service. This work is validated by the chain service and the fork choice store. And yeah, so and then we load the node with basically a proposer key and an attestation key, which is basically just like the XMSS based like tree we're talking about earlier. So uh, one of the keynotes with like XMSS or like LeanSig is you're basically pre-generating, let's say like 8 years worth of keys. And once you use the key once, you can never use it again. So separating these into basically like two trees allows us to further optimize our usage of the keys and like also simplify our stack quite a bit, which is nice. What's been hard in practice? So I would say spec drift. We would finalize a spec, but then one of the challenges is like we find like a breaking bug or we find like a really big performance bottleneck which we have to patch, and coordinating that change between at the start it was 3 teams, 4 teams, 5 teams. I don't even know how many teams are at this point, maybe 8. Coordinating that change between multiple teams and basically like getting them to the state where they have a stable image we can run on DevNet has been somewhat challenging. So an example of this is, let's say we have a state container with n fields. If we switch one field, it totally like breaks interoperability between the clients. So we've had issues in the past where it's like one client didn't update on time and we started a DevNet, and then it's like, why is everything failing? Or even like one line could like totally break interoperability. Um, so testing in reality is not always the easiest. We build these specific fixtures and test cases based off like theory, but oftentimes you don't catch edge cases unless you actually run the manual DevNet itself, which running into these problems can sometimes be hard to debug. I would argue the work isn't always sexy. Like every DevNet, we're incrementally building on the last DevNet. The goal of this is to ship very fast. But oftentimes, if like there's one misalignment between clients, it can be really confusing to like figure out where is the problem and identify that. We are working on tools like Better Block Explorers so we can like visualize this, but one line can totally destroy a client. So that's a problem pre-existing clients have to deal with, and that's also a problem that seems like it will always exist. What I would watch out for is like the object model. Will DevNet 4 will the semantics we think will work in DevNet 4, will they work enough to do in future DevNets, or will we basically like completely throw that idea out? Unless we try it on a DevNet and get those numbers, we basically like we think it will work, and of course we're always doing what we think is the most optimal way forward. But unless you test this on a DevNet, you have no real backing, right? So it's like like the researchers and some members of the client teams are like, we really believe in this for DevNet 4. We run a DevNet, maybe that pans out, maybe that doesn't. One constraint is like, currently we have 4-second slots. Can we really generate all the proofs and like distribute that to all the validators around the world in 4 seconds? This can be quite challenging, as currently even in the beacon chain, for example, Australia has a problem getting attestations gossip to them in time to like finalize the block. So that can sometimes be challenging, and we're being quite ambitious here. I wouldn't say we have like one for one DevNets with like mainnet, of course, but we are doing experiments. And then it's like, how will these dedicated like aggregators will roles work out, and like how will these duties like actually finalize? What makes sense? That's another thing that will be answered with DevNets. And then stability. Uh, One of the problems is like, uh, are we confident in this DevNet or this change? For example, in DevNet 3, that's been running for quite a while. We've been doing many iterations of that. But some of the problems is like, um, I guess with like a lot of problems, you'll get it to where it will work to, let's say, 1K slots, but then it starts breaking down at maybe 10K slots, 20K, 100K slots, maybe a million slots. And it's like, do these experiments actually work in reality? Are they stable? Uh, these are all things we have to like watch out for as we're working. So I was talking about it like client architecture tracks, but I thought I'd also go over some research tracks because in the last EPF, a lot of people who like worked with Ream were really interested in the research path and contributed to it. So I think going over those would be quite helpful. So, for example, like Poseidon Crypto Analysis Initiative, uh, earlier in the DevNets, we were using Poseidon 2, and what we discovered is it's not as quantum resistant as it was. I forget who did the paper. I think it was like uh, ETH Zurich. They released a paper recently where it's not as quantum secure as we thought it was. So for DevNet 4, one of the reasons why it's delayed is we're basically like switching the backend of LeanSig and LeanVM to use Poseidon 1 instead, which currently we believe is a lot more quantum resistant. Hash-based multi-signatures, as I said earlier, this is basically like if you have a validator, if you're signing any object, this is the scheme we're using. PQ signature aggregation with ZKVMs. This is a work in progress. I would argue one of the biggest things this is focused on is like an optimization problem. Well, I list examples like SP1 or OpenVM. LeanSig is as simple as it can possibly get for our specialized case. And I believe that with the signature scheme for LeanSig, which is basically like this above, that we were confident with. Once we set Lean VM to use that configuration, we're only able to get around like 50 signatures per second uh, with our like expected parameters for the cryptography. So it's like hopefully through like regressive aggregation and having a lot of aggregate committees, we could boost the validators numbers up to like something we think is reasonable for decentralization, and then formal verification. Um, as I said earlier, one of the goals with like the whole lean effort, there's a lean execution effort and there's a lean consensus effort, is just simplifying the critical path so we can verify Ethereum secure. The more complex the critical path is, um, the more wary we have to be. So having a simpler critical path for Ethereum is just more, I guess you can mathematically verify its security, to a certain level, I believe. I don't do formal verification, but I guess that's nice for people to sleep on. God bless. So other tracks is peer-to-peer networking. So there's pushes for like Gossip Sub 2, and how do we make like 4-second slots work with like a million validators, which at this stage, who knows if it's possible. And as I said earlier, there's also efforts to like fully replace libp2p with a custom stack optimized for Ethereum's use cases. There's a lot of work there, and I guess if you guys are going to like ECC or ETH Brussels, there's probably a libp2p day where you can learn a lot about like networking concepts like that, and also like basically like the state of the art gossiping mechanisms people are talking about. So I'd recommend you go into those workshops. And then a tester proposer separation, that's been talked about a lot. Could we basically prototype that in Lean? That's something we're looking into. And then fast finality. A lot of these research paths are fairly complex, so having a testbed we can quickly iterate on with like multi-client devnets is, I think, very beneficial for gaining a confidence for mainnet, which is very cool. Whether there's a lean fork or it's incremental upgrades of the beacon chain, I think this work is really beneficial. So I guess like some questions that you might be asking is like, which boundaries feel stable enough to standardize across the clients right now? I would argue probably the only thing is super fundamental things like SSC, which is basically a serialization scheme. Other than that, like there are talks of us potentially changing the hashing scheme from SHA-256 to Poseidon to make that even more ZK friendly. So honestly, I don't even think anything's stable enough to like say it's like we're gonna keep it for like 5-10 years. Well, the initial dev nets are built off a lot of like the stacks and technology of beacon clients. All of that's up on the table for like research and potential improvement. As I said earlier, one of the goals was creating like a concise and optimal platform. Well, that is quite an ideal goal. I think it's quite noble. So, where should proof generation live? Should your watch be able to generate a proof? Uh, should it be in some validator loop? Who should be responsible for this? Should we just offload it to some like super warehouse, like a supercomputer? That's up for debate. I guess currently block building is kind of like that. But for lean, one of the goals would be that like a smartwatch could validate blocks. And then what would you optimize next? Latency. Um, so for this, it would probably basically just be like, I guess, fully going into the like recursive aggregation path and seeing like how many validators we could scale this to, while maintaining our goals of like being post quantum secure to some like n qubit. I think like right now we're targeting 128. Uh, if this architecture had to survive real opera tomorrow, what would you change first? Well, uh, we're so far from that I guess that's not even a real question. So, and then for the reading, I recommend people to look into Lean Roadmap .org. It was made by the reading team, and it basically has like everything you could possibly need to get up to date, whether that is research or learning about Lean as a whole, joining like the Telegram to participate in conversations and join DevNets. It's open to anybody who wants to join. I guess as like the founder of the EPF said, his name was Piper. He was my mentor originally. He basically said like the doors are like laughably wide open or something. I'm sure Mario can correct me on the exact quote, but it's like the doors to participate in Ethereum are like ungodly open. You just kind of have to like show up. For Ream, if you want to like try to run Ream, try to run a DevNet, we have like a quick start guide and we have some like CLI option documentation. Then if you want to look into our source code, it's at our GitHub here. And then, yeah, I believe that is the whole thing. So I will close this.
Yes, thank you so much, Colby. And yeah, Piper, I think he used to say it's comically wide open. Like it's so easy. You don't have to break into the door. You don't have to try to unlock them. They're just so wide open. As yeah, as one would just want to work on anything out there from different domains for the Ethereum protocol. Thank you so much, Colby. We have a bunch of questions that we collected in the chat here. Let's get over those in next like 10 minutes. We have 10 minutes to go, so I think the perfect timing right now, and we still have everyone here. The first questions go back to the network part. Or maybe actually, like there is the first one was about a DevNet cycle, and now like there is a DevNet cycle which is just like the next hard fork sort of cycle where new EIPs get like in each DevNet we add a new EIP that's implemented and tested like cross client. But maybe there it was more you could talk a bit more specific about like the DevNets that you are doing within Lean, which are separate from like the current core development, but as your own prototypes, like what sort of like DevNet testing you do and what's the process there?
Yeah. Oh, so for sure. So currently all the, I guess, DevNets are coordinated on the Lean Ethereum/PM repo, on the Lean Ethereum/PM repo, and the Lean Ethereum Lean spec.
Recording has stopped.
Uh, oh, okay. So currently all the teams are working on the same DevNet. So like we all coordinate on calls on tomorrow on Wednesday on like what are our thoughts on how everything's going. And through that, we basically decide what we're going to do next. And then work is done on basically like updating the spec and also creating like a formalization document of like what are our goals and what are our outlines in the project management repo. Currently, all the teams are working on the same DevNets. Sometimes there's ideas of maybe it would be worth of working on another DevNet in parallel, depending on what is happening. Currently, all of them have been sequentially just due to the work. But yeah. Right now, there's no like formal E process. It's more like, oh, do we think this is like, is this the next most important thing to like achieve our goals? And then we just like spec it and then implement it across all clients. And then we're like, let's run it and see if it works. And then like a lot of the time it just totally fails. And then we debug it and fix it. And then we get our numbers and then we run it back and do the next biggest thing we can think of.
Awesome. Thank you, Colby. So yeah, there was the part, the question about networking, like whether this is something specifically designed for Ethereum. I know that like we're talking about the lit peer-to-peer, but maybe what are their like what my question I would reframe it a bit. Maybe what are the like peer-to-peer changes compared to the current consensus, or how we make the peer-to-peer more lean? What are some fundamental changes, if anything, like gossip happen, everything?
For sure. So, like, just to preface this, like lean P2P or like P2P2 for Ethereum, whatever you want to call it, uh, it isn't my specific domain, but basically the understanding of it is currently one of the biggest bottlenecks in Ethereum is efficiently transferring like data between nodes. And this is one of the biggest bottlenecks from like shortening finality or shortening the slot time. Is it's like, can we reliably get all this data to all the nodes on the network? So the gossip stack and the tech like is pretty generalized, and it was built for, I believe, like what was it, like interplanetary file system, like IPFS, which is like basically like a DHT where people just share files. What if we use like the most modern research to basically build like the most efficient way to like transfer these blocks and attestations between nodes to shorten the like slot window basically. So yeah, instead of using like a generalized framework like libp2p, which is used by multiple protocols, building one optimized for our use case.
Awesome. Yeah, thank you. So that was the question that Abim's also followed up. And okay, where do the ZKVM proving stages fit into the Lean client? So going back to the stages there, are the proving stages the biggest bottleneck?
Are the so currently I'd argue it is the biggest bottleneck because for each validator creating its attestation to the block, that can be fully parallelized over the entire validator set. But currently creating like the aggregate signature with our like minimal ZKVM, which is like lean VM, we can only do like 50 signatures per second. Last I checked. So we are playing schemes of like having like an aggregate of that. So it's like have like 50 aggregators create an aggregate and then aggregate that again. So you have like I guess like 50 times 50 each, which is like isn't that just 50 times 50? But one of the problems is we don't want to like compromise on decentralization. So it's like I would say it is one of the biggest bottlenecks and current research challenges that we are facing. So 100%.
Okay. So there was a question about the equivalent of execution layer, maybe for more context, if folks haven't looked into the Lean roadmap. What's the equivalent of the execution layer in the Lean upgrade, or these updates are meant for CL only?
So currently, what I'm working on is Lean consensus. Uh, for the execution layer, I don't believe we're going to be like implementing new clients. My current understanding of the goals for lean execution is how we could possibly like simplify our current execution layer, but also like basically have a GPU farm where you could create a ZK proof of like verifying the block so that like low end hardware wouldn't need to do that themselves. And then people who want to prove the whole block with their hardware can do it. So it is a bit of like, I guess, a different route. And that route is more of like fun, I guess, like holding competitions for basically like ZKVM teams, such as like SP1, Risk Zero. There's a ton others, and also running things like I forget what the website was, but it was like basically like how fast can we prove a block in Ethereum, and it was basically like every ZKVM team tried to like prove every current day beacon block and in turn execution block in real time. So stuff like that is more of the like lean execution side of the whole lean effort, where the lean consistent effort is a lot more of like uh, trying to figure out how we could like I guess post quantum the consensus layer, if that makes sense. So it's like different tracks basically.
Yes, different parts of the protocol. And yeah, this is the consensus. In the current Reams implementation of Lean, which parts of the spec still feel accidentally complex rather than fundamentally necessary? And do you think those will get simplified at the protocol level or just absorbed into clients over time? So yeah, how do we feel about the complexity of Lean, which is a bit ironic there?
So I guess we could kind of like break this into different sections. In terms in terms of something like cryptography, often that's done by like very specialized cryptography teams at the EF or funded by the EF. Sometimes it's a mixture of both. So, for example, like the XMS research has been done by the EF. Um, so, like Lean Sig, Lean VM, all that research for doing like post quantum signatures was done by them. These researchers who also like implement these clients also like work on optimizing these. So the same ideas apply from the beacon chain where like these specialized teams will build these very audited libraries that clients can use. So from our angle, we don't have to deal with a lot of that complexity. I would say a lot of our complexity would probably be like the networking stack. Uh, in terms of like fork choice and state stuff, a lot of that is just like optimizing us it. So I would argue the most complex thing is like dealing with like the P2P stack in a generalized framework such as libp2p. Potentially like with it's like Ethereum P2P, so to speak, uh, that will become a lot more simplified. But there's always the challenge of like P2P building a really good P2P protocol is really hard. So like properly debugging that would then cause like all these new problems of then we're testing like 10 different ETH P2P implementations against each other. So I think we're probably going to avoid that now just because like the complexity of testing a new P2P stack is so high. And we're just going to focus on like the complexity of like basically like in Oppenheimer, you had like Oppenheimer who's like, this is theoretically possible. And then you had like the research team where it's like, we just smashed two atoms together. Uh, I'm on like the team that's like, yeah, we can split an atom. And like the research team's on that side. Wacky analogy, but hopefully that answered the question.
Awesome. And one last question from Lee. How long does it take to generate the public key of the XMSS signature scheme?
Uh, so clients can choose how many, I guess. So I guess you have like so you have like your public key, and then you have like a a leaf that you would sign this like a block with in the tree. So generating, like proving a block can be done like super quick in like no time with no CPU. But generating these public keys, you basically would decide like in how many years would you want to refresh these keys or generate more? I'm assuming a lot of people would want to generate like 10 years worth of keys, and then you would basically need to run your like M1 laptop for like 10 hours, and then you wouldn't need to worry about that burden for 10 years. So it's basically just like scalable depending like how often you want to like refresh your keys for your validator. It could be like as quick as a minute, but then like you're gonna run out of the keys you generated fairly quick.